Now let's move on to the fourth law. The fourth law states a to the power 0 equals 1, and a being any number. So what this means is any number raised to the power 0 is equal to 1. Now that means if I say 2 to the power 0, or whether it be 3 to the power 0, or 10 to the power 0, or even a very big number like, let's say, 1,253,312 to the power 0. I just chose a random number there. Even negative numbers, minus 5.32 to the power 0, or minus 10 to the power 0. Any number, if the power is 0, the answer is always 1. The question now is why? Why any number raised to the power 0 is 1? Even 0 to the power 0, this is 1. Now, this is the general case. Generally, 0 to the power 0 is 1. But there are some special cases when you go for advanced concepts in mathematics where 0 to the power 0 is considered to be undefined. But generally, when we consider any number raised to the power 0 is 1. Now, the question is why? Why is a number raised to a power 0 equals 1? And how is that possible? What is the logical argument behind it? So to answer that, let's list the powers of 2. 2 to the power 1, that is 2. 2 to the power 2, that is 4. 2 to the power 3, that is 8. 2 to the power 4, that is 16. And 2 to the power 5, that is 32. And it goes on like that downwards. And let's do the same with two more different bases. So let's go with 3 now. 3 to the power 1 equals 3. 3 to the power 2 equals 9. 3 to the power 3 equals 27. 3 to the power 4 equals 81. 3 to the power 5 equals 243. And that goes down forever as well. Let's go for one more base. 5 to the power 1, that is 5. 5 to the power 2, that is 25. 5 to the power 3, that is 125. 5 to the power 4, that is 625, and so on. Alright, now let's go ahead and see the pattern of the answers from backwards. Now if I go from the fifth power of the second base, if I go here and say 2 to the power 5 is equal to 32, from 32 to get to 16, you should divide this by 2. And from 16, if you want to go back to the previous number would be, again, you have to divide by 2. From the previous number to go to the one before number, we have to still divide that by another 2. From here, if you want to go to the previous number, again divide that by 2, correct? 32 divided by 2 is 16, 16 divided by 2 is 8, 8 divided by 2 is 4, 4 divided by 2 is 2. According to this pattern, the number before 2 should be 1. And that should be then 2 to the power 0 in the same pattern of powers. Now let's have a look at the base 3. Let's start from 243. To get 81, you should divide this by 3. To get 27, you should divide again by 3. To get the previous number 9 from 27, you have to divide that by 3. So this clearly is a pattern, right? So to get the previous number, we have to divide by 3. So to get the number before 3, we have to divide that by 3, and 3 divided by 3 is 1. And in that same pattern, if you look at the left-hand side, the left-hand side has to be 3 to the power 0. I think now you can understand how it's going. Let's go to base 5. 625. If you want to get 125, you divide by 5. From 125, if you want to get to 25, you divide by 5 again. From 25, if you want to get to 5, you divide by 5 again. So if you want to go to the previous number, you divide that by 5. 5 by 5. So 5 divided by 5 is 1. And in the same pattern on the left hand side, power 4, power 3, power 2, power 1, now the power has to be 0. So we see that 2 to the power 0 is 1. 3 to the power 0 is 1. 5 to the power 0 is 1. So from this you can understand whichever the base you take, the pattern is going to be dividing by the same base. So this logically tells you why any number raised to the power 0 is 1. And for the final law of indices, which is the fifth law. It says a to the power minus m is 1 over a to the power m. Now, what this means is that when the power is negative, if you switch its position from numerator to the denominator, the power becomes positive. Let's have a few examples to understand this better. So let's say 2 to the power minus 3. Now, without the help of a calculator, you won't know what 2 to the power minus 3 is if you were to try mentally. I mean, you can think of 2 to the power positive 3, which means 2 times 2 times 2, which is 8. But 2 to the power negative 3, how will you multiply 2 negative 3 number of times? You can't do that, right? So what this fifth law tells you is how to do it. So basically 2 to the power minus 3 can be considered as 2 to the power minus 3 over 1. By default, there's a denominator 1 for any number. You take any number, there's always a denominator 1 by default. So you're going to make a reciprocal. So you're going to put the denominator to the numerator and numerator to the denominator. So you're going to do upside down. So when you do that, the powers, the sign of the powers will change. So 1 over 2 to the power 3. So the bottom line for this fifth law is that when you reciprocal a fraction, the sign of the powers will change. We'll discuss about this in another few examples. As for this one, this is 1 over 2 to the power 3 is 1 over 8. This is 0.125. Now we can easily find the answer to the negative power. So 2 to the power negative 3 is actually 0.125. So let's go ahead and look at a few examples, like let's say 3 to the power negative 4 times 5 to the power negative 2 divided by 4 to the power negative 6. Now, as I mentioned, all of these powers are negative, right? So minus 4, minus 2, and minus 6, these are the powers. If they are all negative powers, when we reciprocal, all the powers will change its sign. So the opposite of negative is positive. So you put 4 on top. So 4 becomes 4 to the power 6. This becomes 3 to the power 4 times 5 to the power 2. All the minus signs have been turned into positive because you put it upside down. Let's look at another example. Let's say 4 to the power 3 times 2 to the power negative 4 divided by 3 to the power negative 2. Now what happens if you do the complete reciprocal, where you put the denominator to the numerator and the entire numerator to the denominator? What happens is 3 to the power minus 2 comes up, so that becomes 2 to the power 2, divided by 2 to the power negative 4 goes down, so therefore it becomes 2 to the power positive 4. But 4 to the power 3 was already a positive. Since you switched its position, now it becomes 4 to the power negative 3. Because it was in numerator, now it's denominator, so the sign should change. So it was already a positive, now it's a negative. And this is not what we want. We wanted to get rid of all the negative signs, not to create new negative signs. So what we do here is that instead of moving 4 to the power 3, we keep 4 to the power 3 as it is, and just move the negative powers around. So you put 3 to the power negative 2 on top, that makes it 3 to the power 2, and you send 2 to the power negative 4 to the denominator, that makes it 2 to the power positive 4. Let's have a look at another example. Let's say 5 to the power negative 3 times 2 to the power positive 3 divided by 3 to the power negative 2 times 4 to the power 2. Now in this case also we have a mixture of positive and negative powers, and as I mentioned in the previous question, we don't need to move the place or the position of the positive power, because when you do that, you change that to a negative. So we keep the positive powers as it is. So 2 to the power 3 stays on top, 4 to the power 2 stays at the bottom. However, we can switch the negative powers. So 5 to the power negative 3 becomes 5 to the power 3 at the bottom. 3 to the power negative 2 becomes 3 to the power 2 at the top. Let's look at another example. Let's say 5 to the power minus 4 times 3 to the power minus 2 times 2 to the power negative 3. How do you do this? Well, all of the powers are negative. As I mentioned previously, there is always a denominator 1 by default. So put all of them down. It will become 1 over 5 to the power 4 times 3 to the power 2 times 2 to the power 3. And one more thing is that You can switch it like this only when there is multiplications around. When there is additions in the middle of multiplications, you can't do that. For example, if you take this same question and if I write it like this, 5 to the power minus 3 times 2 to the power 3 over 3 to the power minus 2 times 4 to the power 2. The fraction that we are looking at here doesn't have any addition inside it. You can swap and you can switch numbers as you want to make the powers positive. But in case if this plus 1 was somewhere here, now this is a part of the fraction, and since addition is involved, you'll not be able to switch it like that. In this case, what you would do generally is you would split the common denominators as 5 to the power negative 3 times 2 to the power 3 over 3 to the power negative 2 times 4 to the power 2 plus 1 over 3 to the power negative 2 times 4 to the power 2. Now you can swap it around, so you can say 3 to the power 2 times 2 to the power 3 here. You take the 3 to the power minus 2 on top, and you put the 5 to the power negative 3 at the bottom times 4 to the power 2 plus here you can just move this 3 to the power negative 2 to the top. That makes it 3 to the power 2 over 4 to the power 2. Okay, so these were some examples that I wanted to show you as to how it works. You may have got this question as to why is nothing happening to the 1? For example, if I had switched the positions of 1 and if I had moved this denominator 1 to the position of numerator, shouldn't the power of 1 also change? That is correct. So this should be power negative 1. And even in the first cases, since you switched the denominator 1 to the numerator, this should also be a power negative 1. But why don't we do that is 1 to the power anything is just 1. Maybe you can write that also as another law. So you can say maybe law number 6. 1 to the power anything is just 1. Because 1 times 1 times 1 times 1 times 1, however many times you multiply 1, the answer is always going to be 1. So 1 to the power negative 1 is also just 1. So that's the reason when we swap it around, we don't do any power changes in 1 because it will eventually end up as 1 again. So 1 to the power negative 1 is also just 1, and same case here, 1 to the power negative 1 is just 1. So I hope you have understood the laws of indices now. So in the next video, we'll be looking into simplifying algebraic fractions by using laws of indices. So I'll meet you there.